Here, tea drink. I wanted to give you an update about your exam grades. I'm going to be completing my video where I do a walkthrough of the exam and going question by question. This is the right answer. This is the incorrect answer, and give an explanation why. Um, I will have that done by the end of today. And at that point in time, that's when I'm going to release that video and make sure that all of the answers that I have keyed are correct so that then I'll release your grades. So expect your grades in that video later this afternoon. I like to do that just so that I can avoid, having any sort of regrades or anything like that. Now, with that in mind, that's kind of the hold up there, and I apologize for the delay on that. Um, I've got a couple of folks who probably want to meet and talk about grading. And to put it simply, your exam grades, every successive exam grade can replace the previous one. And what I mean by that is exam two, if it's higher than exam one, will replace your exam one grade. Exam three can replace two. It won't replace one, but three can replace two, four can replace three, and then the final exam can replace all of them. So that's a super important thing, I think, to remember if you're looking at or when you look at your exam grade, if you're like, I wanted to do better, I got an 80, but I think that I can make an A. Yes, 100% you can. Um, in addition to that, I posted a practice exam for this last one, and I'm going to post another one of those, but I'm going to get it up earlier in the testing phase. And I mean, before the next exam. I apologize for taking so long to do that, but I will get that up. So then you have an idea of like, okay, this is the sort of question that he's going to be asking. I think that will help folks because what I noticed as a quick trend was the people who did the practice exam, they typically did pretty well on the actual exam. Now, with that in mind, we don't have an exam for, I think it's 2.5 more weeks. I think it's a Monday in November. So we've got a little bit of time, but remember that's exam number three, and exam number three can replace your grade on exam number two. So when you get this exam grade a little bit later today, keep that in mind. Okay, so I hope that, I might have to knock my video off for just a minute because my wife is also doing a meeting. And so sometimes, I mean, yeah, so there might be some delays in our internet connection. Today, what we are talking about, and we are getting moving on states of matter. A gas is a state of matter in which atoms or molecules have enough energy to move freely. The molecules come in contact with one another only when they randomly collide. So it's almost like my coffee mug in this timing cube. These are particles within a gas, and they're floating around, but they're only going to hit each other when they just like happen to bounce off of something and then bing, boom. Okay. So now a liquid is a state of matter in which atoms or molecules are constantly in contact but have enough energy to keep moving positions relative to one another. So it's almost like this is the liquid and they're in contact and they're moving about and they're moving around. My little square that you see me in is the container, of course. Then next up is a solid. A solid is a state of matter in which atoms or molecules do not have enough energy to move. They are constantly in contact and in fixed positions relative to one another. So here, that's a solid. We can wait. Nothing's going to happen. Now, could something happen? Yeah. Erosion, for instance, that could take place. If it rains, water might run over something and basically degrade it away. But that's about it. I thank you, Kevin, for reminding me to share my screen. I was giving you just wonderful explanations, and I'm really happy that I didn't share my screen because then, yeah, there we go. Because then you could see a better visual of everything that I was demonstrating. But Kevin, thank you very much. So these are the definitions: a gas, a liquid, and a solid, and the different amounts of energy that they each have. Now, to view those, we've got two different depictions. Up top, we have kind of the macro view of it. So where you would see a solid, a liquid, or a gas. Here's a solid and liquid and a gas. Now, I think that this last one is really great because it's it's optimistic. Because this container right here, this beaker, this 100 ml beaker is full with gas, much like, optimism, half full, half empty. Well, this one's full. It's full of a gas. Now, this liquid ice, or sorry, this solid ice, all of the molecules that make that up, there's extremely small movements, very, very few movements because they basically have a limited or virtually no energy. Whereas a liquid, if you were to track one of these balls and just sort of like, I'm going to try that right quick. If you look at my kind of drawing, I'm tracking one of them. It's going to move around. It's going to come in contact with others. Um, Whereas a gas, those gas or the molecules that make up a gas are in constant movement. And if you're to track one of those, I mean, they can go on one trajectory, no problem. And then if they hit a side, they're going to bounce and hit something else and boom, 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 boom. That's what a gas is going to do compared to a liquid and a solid. So I think that these are probably realistic experiences that you've had with liquids and gases. And I think that it's kind of easy to imagine. Well, a solid, I always think of a brick. If I have a brick, nothing's going to happen to that brick. It's going to stay a brick until I decide that it's not going to be a brick and I break it up. Now, where we go from there, the liquid, if you pour a liquid, it's going to spill everywhere. So these are three different states of matter. And these are our macro at the top here. Macro are our large view, and then our molecular or our micro view of these different states of matter. Now, some more definitions and more things to think about with respect to these different states. A solid is going to have a fixed shape, and it's going to have a fixed volume. If you take my timing cube, and this is something my wife got me a few years ago for Christmas, what it is it's got a little timer, and it's got a battery, and then it's got different time designations. So if I'm going to focus on something for 10 minutes, I flip it this way, it beeps, and then it has a countdown timer for 5 minutes. This cube right here, this is a solid. And the molecules that make this up, well, they're going to stay where they are. This is going to retain this shape and the space or the 3D space that it occupies. It's going to retain that until there's something that changes that, until somebody comes along with a hammer and crushes it or something like that. This solid will not kind of melt away without some sort of energy being input. Now, a liquid, okay, if you think about like this coffee mug, if I took this coffee mug, I poured coffee into this, or into this beer stein right here. Well, the shapes that these have are slightly different. The coffee mug is perfectly cylindrical. This beer stein will kind of, it flutes out, or it kind of spreads out at its base for the purposes of stability there. Now, if you get 500 milliliters of water and pour that into this coffee mug and pour it into this beer stein, the shape that liquid is going to occupy is going to be different. I always like to visualize that and just say, okay, here is X amount of water. And if I put that into let's go with everyone's going to celebrate here with you're getting a champagne or a sparkling grape wine flute. We're going to pour that into there, and it's going to have a shape that looks like this. Compared to if you pour it into a martini glass or a water glass, pour it into here, and well, it's going to occupy that liquid will take on a different shape depending on the container that it's in. Then last but not least is a gas. Gases have variable shapes and variable volumes. Now, if I've already told you the story, I apologize. But when I was in 6th grade, there was a student who They got a stink bomb. And a stink bomb is a volatile, or it's got a sulfur containing compound, and she cracked it open in the bathroom. And first, that gas filled the bathroom. The shape that that gas took on was the bathroom. Then it got into the ductwork. Now all of a sudden, the shape that that gas took on was the bathroom and the duct system. So when you think about the shape, those are different. When you think about the volume and the space that those two different um, rooms or places occupy, well, the volume of the bathroom is less than the volume of the ductwork. And then eventually it occupied the entire school. So the shape of that gas was the entire school. And then the shape of that gas was, or sorry, the volume was the entire school. So we have these variations between solids, liquids, and gases. A solid has a fixed shape and a fixed volume. A liquid has a variable shape, but a fixed volume. A gas has a variable shape and a variable volume. I always kind of think about this almost as like a gradient. Solids have no flexibility. Gases have nothing but flexibility in terms of their volumes and their shapes. All right. Now, this right here is a nice illustration for how to do or how to look at gases and how they change. Just so, okay, cool. So here what we have is a substance that is in a closed container. Okay, so all those blue balls represent molecules. Now, I'm going to toggle through the different states of matter. We've got a solid, which, there we go. All of those blue balls are pretty limited in the space that they occupy. Then we're going to make it a liquid. Okay, all those blue balls, what do? They spread out on the base of that container. Then, if we go to a gas, oh man, they're everywhere, which kind of makes sense because if you think about like boiling water or something like that, what happens to the steam that comes from boiling water? Well, it fills the air, it fills the space. In this case, we're talking about neon specifically as our atom, but if we were to change it to water, let's make water a solid. Okay, those are ice cubes at the molecular level. Liquid water at the molecular level, and water vapor, excuse me, at the molecular level. We've got lots of them kind of going crazy and they bonk into each other and they change. Okay. Now, with that in mind, with our toggling between those different options, I've got a top hat question for you. And we got 30 seconds for this top hat question. The question reads, what do you expect will happen to the blue balls as heat is increased? Okay. So my default is we're going to go to that neon in its solid state. And then we're going to adjust the heat. What do you think is going to happen? So our starting point is neon as a solid. So the way that we saw it whenever we first opened that slide. What do you think is going to happen to those? You got 30 seconds. Now, this isn't something, there's no correct answer for this. I'm looking for responses.
For example, you could look at it to see maybe where a particular expert is struggling, if you had an idea that they were. But you could also use it to see maybe where,
I'll put another 15 seconds on there just to get some more responses.
Really a way to use the, AI technology to analyze the data that we already have so that we can make it more useful.
All right. Let's see what we got. What are our responses?
Well, and I don't want to keep you
Okay.
because I know everybody's busy
Okay.
and we're tired.
As the heat is increased, move more but stay at the bottom of the container was our second highest mark. Move more but and distribute throughout the container. Let's go ahead and go back to that. Let's see if we can do this. So I'm going to jump ahead to my next slide, but then I'm going to exit full screen, go back to this. So I'm getting neon as a solid, and I'm going to increase the heat. Okay, so we increase the heat and we'll increase it a little bit more. It's going.
You're good.
And I didn't include, I was looking for what everyone was thinking about this. I didn't include a detail of like how much I increased the heat. So everyone seemed to answer that answer option D, or the majority answered option D, where it distributes throughout. And you know what? As we continue increasing the heat, we are indeed going to see that.
So it's important.
So this is going to go from a solid to add to the chat. What is the movement throughout? What does that most look like that we previously saw? A solid, a liquid, or gas? Gas, perfect. Perfect. Absolutely. It looks more like a gas. So, we're kind of looking at a transition of sorts.
Oh, yeah.
How do you think that you describe this transition? Or what are we transitioning between? Different blanks.
There you can tag.
What are the blanks?
I also have included this in the
Close. Solid to a gas. Different states, different phases. Absolutely different states of matter. We're doing what are known as phase transitions. So we're transitioning between these different states of matter. Great job, Caitlin, Gabriel, Corazon. I appreciate those contributions. Thank you so much. Those are great. Now, this is a depiction of what's taking place there. This is what's known as a phase change. So this graph shows us this graph is known as a phase transition. And what we're looking at is how this goes from, let's look at our axes. So our x-axis is increasing energy content of the sample. So we're adding energy. Now let's look at some of the plot throughout this, or some of the plotted materials throughout this, or some of the information that's plotted. We've got in the lower left-hand corner, we've got a solid. And in the upper right-hand corner, we have our gas. On our y-axis, what we're seeing is the temperature increase. So I'm going to put this at 0 to infinity, just to throw something high up there, and then increasing energy content of the sample, also from 0 to infinity and beyond. Okay, so on our y-axis, we're seeing what happens when we increase the temperature. And these pictures right here on the left-hand side show some solid water or ice. And then what happens whenever we heat that ice? We're going from what's shown on this thermometer here is 0 degrees Celsius. Then this is 100.0. It looks like it's 1,000, but it's 100.0. What's 100.0 with respect to water? It's our boiling point. So we're going from this ice where it is frozen, the melting point, which is 0 degrees Celsius, all the way up to the boiling point. Now, what that means, there's a couple of pieces of information that you can take from this. If we are at a very low temperature, actually, I got to change my axis, not from 0. I'm going to go from, well, I'll leave it at, so my scaling here would be on Kelvin, but this is showing degrees Celsius. So if I take the temperature below my melting point, what does that mean for my solid? What phase is it in? If you get a solid, basically my question is, if you get ice at 0 degrees Celsius, okay, and then you drop the temperature to negative 35 degrees Celsius, what is the state of this ice? Is it a solid, a liquid, or a gas?
Oh, hey, Kylie.
It's a solid. It's still a solid. You're absolutely right. It remains a solid. At negative 35 degrees Celsius, yeah, it's just cold. And I mean, I can't help but think about the 2003, yeah, I think it was 2003 or 2004 Outcast song, Hey Ya, what's colder than cold? Ice cold. Basically, this is taking a solid and making it colder. It's still ice. Now, with that said, when we heat that solid up, when we heat it up to 0 degrees Celsius, we reach the melting point right here. And what we have there is some of that solid that's melting and then some of the a liquid that's kind of freezing. When we go above that melting point, that's whenever we have our transition, or we have more of that liquid appear. So between a melting point and a boiling point, that's when your liquid form of water or whatever substance is going to exist. Now, when you get above that, above your boiling point, now you're going to transition from a liquid to a gas. Now, there are some important terms that I want you to know about these different places. So I'm going to clear all my drawings off of this, and I'm going to highlight, or I'm going to put check marks by terms that I want you to know. Melting and freezing. I think everyone's pretty comfortable with those. Then vaporization and condensation. Okay, so some of these terms you've probably heard before, and you're probably fairly familiar with, but these are what are known as, oh, that's the disappearing pen. That's it. That's how it works. Sorry. Vaporization is when a liquid transitions to a gas. Condensation is where a gas goes to a liquid. Melting is where a solid goes to a liquid. And freezing is where a liquid goes to a solid. Now, this horizontal line right here is one that's worth noting and worth paying attention to, because that's where your phase change takes place. You have to increase energy. This is why if you go outside when it's 32 degrees out, it's not as if all water spontaneously freezes. That's not what happens. You know that. You've observed that does not happen. Now, that's because additional energy has to either be taken from or added to. Now, we have another way of depicting a phase change diagram. That is like this. Okay.
Oh, yeah.
We're still talking about solids, liquids, and gases, but it's changed a little bit. What's different on this than our previous graph? Well, here, I'll toggle back and forth between them. Let's think about our axis, our y-axis. Our y-axis of this graph is temperature. Okay. Then our y-axis on this graph is pressure. Okay, so those are different. The x-axis of this graph is temperature. So we're still concerned with temperature, but it's it's a little bit different how we look at it. Okay. Now, what this phase diagram shows us is a relationship between pressure and temperature, whereas the previous one shows us a relationship between input of energy and temperature. Now, this shows our different states of matter, our solid, our liquid, and our gas. And then there's one other one known as a supercritical fluid. So this diagram right here, what's important to know about and process when you look at a graph like this is to ask yourself the conditions that you're kind of talking about. So let's say that I had a solid right here where I've just drawn an X. And let's say that my temperature was, let's go ahead and say it was 350 Kelvin. Then let's say that my pressure was 1 atmosphere. What would happen if my pressure dropped to 0.25? What state would my material, my substance be in? If it goes from 1 atmosphere down to 0.25, do I still have a solid on my hands? I have a gas. You're absolutely right, Caitlin. I've got a gas there. Did I change my temperature? I didn't. I kept my temperature the exact same.
No,
What changed was the pressure. So now let's imagine that
when
I go back to my original reference point. And so I'm at 1 atmosphere pressure, and then I increase my temperature. What would you expect to happen if you had a solid and you increase the temperature, but held everything else constant? What's the phase change, or what's the word you would use to describe that? It would melt. Absolutely right, Caitlin. So this is going to be melting. We kept the pressure constant, but we increased the temperature. Okay. And just like what you see whenever you um, basically try to, if you were to put on water in a pot on your range oven, if you increase the temperature even more, so we arrived here and then we continued increasing the temperature and we arrived here, what's going to happen? It's going to go from a solid to a liquid. Exactly. It's going to vaporize. Now, with that said, if you were to, let's say, get to this point and drop the pressure, you wouldn't have to change the temperature, but instead you would end up right here as a gas, and um, that would be a vaporization as well. So whenever you look at a graph like this and whenever you're processing this, it's important to know a couple of different things. Now, it's important to know, like, and you will see on your exam and quizzes and stuff, questions asking about these things. So you start here and you go here. What is that known as? That's melting. Okay. You start here and you go here. That's vaporization. Okay. What about if you start if your material starts as a gas and then you drop the temperature a lot and you end up here as a solid? What's that known as? Where you're going from a solid to a gas. A solid to a gas is known as, I'll give you a little bit of a hint. Um, my hint is they're a very popular band about 25 years ago. And I think they're still popular. My hint is that also that they're from Long Beach, California. And my last hint is that the lead singer is deceased and his son is now leading the band. Spoiler, it's not Van Halen. Sublimation. Kylie, perfect, 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 perfect. That's right. It's Sublime was the band and Sublimation. So when we're going from a solid to a gas, sorry, I need to go solid to a gas. This is sublimation. When we're going from a gas to a solid, this is deposition.
Is it the IT support tool?
And if I said that incorrectly previously, I apologize. We're going from a gas to a solid is deposition, from a solid to a gas is sublimation. Now, with that said, if you've ever been to a haunted house or a Halloween party, you're probably actually familiar with sublimation. And how are you familiar with sublimation? What's the stuff that you can buy at the grocery store that's super cold and it makes everything oh so much more spooky? Close, dry ice. Dry ice sublimes. It goes from a solid straight to a gas at room temperature. So dry ice is a great example of this. Now, when we go from a gas to a solid, that's deposition. Solid to a gas is sublimation. When we go from a gas to a liquid, that is known as, here, let me erase some of my markings. I'm going to erase dry ice. Everyone's good with that. When we go from a gas to a liquid, that is condensation. And then from a liquid to a gas, we have what is known as vaporization, which I think that that's almost intuitive because you know about, well, we're making water vapor when we boil water, vaporization. Then a solid to a liquid, that's everyone's favorite because it's kind of easy. You see that, that's melting. And then a liquid to a solid is freezing. Okay, so those terms, I want you to know those terms. I want you to know those transitions so that when you have questions about those, for example, on the top hat question that we're about to have, that you know the answer to them. Okay, I'm going to clear all my markings and go. We've got a question. Which process is indicated by an arrow? So we've got an arrow that's going to show up on one of these graphs, and I want you to answer it. You have 1 minute beginning now. Oh, shrink that. Yeah, there we go. That's better. Solid going to liquid. Is that freezing, melting, sublimation, vaporization, condensation, or sublime rules? There is one correct answer. There might be two true statements, but there's only one correct answer. Okay. 7 seconds. Let's see what we got. I'm confident. I tell you what, if everyone got this right, I'm gonna put it all out there. If every person got this right, there's one bonus point on the exam. If every person gets it right, it didn't happen. Not this time, but next class, there's going to be a top hat question that if every person gets it right, that's a bonus point on the exam. Just one bonus point, and it's not going to be for every question. But the correct answer here is melting. For those of you who put sublimation, vaporization, and freezing, incorrect. Freezing, we're talking about a liquid going to a solid. Sublimation, we're talking about a solid going to a gas. And then vaporization, we're talking about a liquid going to a gas. So those are transitions, but they're not the right ones that we were looking for in this question. But keep in mind, next time, want to stay clued into those top hat questions and be ready for next class period. What is indicated by this arrow? Okay. I tell you what, if we get 100% on this question, 100% on this question, half a point. Half a point. 100%. And that doesn't mean nobody answer. I hate to throw a bunch of terms on it, but it's like you got to have like 40 people answer. It's kind of what I'm thinking, at least. Got 35 seconds left on the clock. It's an old high school shot clock or college shot clock. 24 NBA shot clock. Okay, what are we going to do? 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 I think we're going to do it right. I think everyone's going to do it. I think we're doing this. Going from a gas to a liquid. I think we're gonna get 100%. Talking about it, I think it's gonna happen. I think that everyone is going to mark the correct answer, and we're gonna see right now. Is everyone ready? I personally am ready. Personally, not stressed, but this is kind of like a movie you've been eagerly awaiting. And our correct answer is close, close. We're going to do it again next time, okay? So everybody, come with your A game on Friday for those top hat questions, okay? Deal? Or maybe not Friday, but Monday, Monday. So then we can spread the word. Let's give ourselves a little bit more time. On Monday, there's going to be a top hat question where everyone's got to get it right. And then there's going to be a bonus point on the exam. Okay, so condensation is the correct answer. When we go from a gas to a liquid, it's condensed. It has formed that liquid. Now, what this all relates to are forces. We've got intramolecular and intermolecular forces. Now, intermolecular forces are kind of like an interstate system. Well, the Interstate 35, what does that take you? That takes you from Minnesota down to Texas. You go through some other places too, but that's between different states. Intramolecular forces are kind of like if you had an intra-state system. I guess that would be closest to your highways. Those intramolecular forces, I'm going to circle this one molecule of water. That's a covalent bond within that one molecule. Intermolecular forces are found between different molecules. So if we look at molecule A right here, I'm going to draw a circle around molecule A. And then here is molecule B. Draw a circle around, or not a circle, but a oblong shape around molecule B. An intermolecular force is represented with these dots, and that's pretty typical of an intermolecular force because it's not as strong of a bond and as strong of a force. The physical state of a solution, of a compound, depends on intermolecular forces. How strong are those forces? Are they very strong or are they very weak? Now, one thing that I would like you to keep in mind is, and actually go ahead and can anyone guess what this molecules A and B are? Go ahead and guess. Add it to the chat. I'm going to count down about 15 seconds in my head.
It's like an etiquette thing too. It's weird because when I put something in.
Perfect. Caitlin, pat on the back for Caitlin. Well done. Water is absolutely right. Water is a substance that has lots of really unique properties. For instance, water has a high boiling point. Water has lots of surface tension, which is why whenever it's the beginning of the summer and you're like, I've been training all season long for my belly flop, it's going to hurt like heck. It's because water has these super strong intermolecular forces. Those intermolecular forces are going to kind of lean on the physical state, or the physical state is going to lean on and be kind of dictated and influenced by intermolecular forces. Now I got to clear my drawings out here. We have ionic and molecular compounds. We talked about ionic compounds. We talked about molecular compounds. I love this image because what this shows is well, a chloride ion, chloride ion, chloride ion, chloride, do. Lots of chloride ions. Then what else does it show? It shows sodium ions. These things pack super tight. And when we talk about sodium chloride, we talk about Na and Cl. And we always simplify it and we say one sodium atom gives up one electron to chlorine, which accepts that one electron, and they're happy. They form a ratio of NaCl. Beautiful. Well, that's part of the story. That's an important part of the story, but that's not the entirety of the story. The entirety of the story is that an ionic solid has extremely strong electrostatic interactions. So what that means is that this sodium ion, sure, it's close to this chloride ion, but it's also close to this chloride ion. It's also close to this chloride ion. We have these, ultimately, this compound has a ratio of 1 Na to 1 Cl. But they're just in this kind of ratio with one another, and they're in very close proximity. They make this complex network. Now, we've also got a molecular solid. Molecular solids have weak intermolecular forces. So here is a CH4 molecule. Here's another CH4 molecule, and here's another. These CH4 molecules basically they have pretty weak interactions with one another. An example of a molecular solid would be something like propane. What do you know about propane or butane for that matter? What do you know about those compounds at room temperature? Well, they're gases. They're gases and they're very flammable. That's why you put them in a canister to ignite your grill or for a lighter. These have super weak intermolecular forces. And so at room temperature, that's enough energy to get that substance to be in its gaseous state. Now, as we go from there, oh, I got to clear all my drawings. Sorry, everybody. We can talk about an ionic substance and a molecular substance. Ionic substances are solids at room temperature. Okay. That's not too much of a stretch because I could go to my kitchen right now and I could get salt and sprinkle it on my hand. Sprinkle the salt on my hand and boom, that's a solid at room temperature. If I were to get that salt and let's say that I put it onto, um, see ya, if I were to put that onto like a frying pan or something like that, and I just increase the heat on that frying pan, what's going to happen? Well, eventually that salt's going to like pop and it's going to land on my skin and it's going to hurt like heck. Another thing that could happen is let's say that I had a range oven that was like super powerful. In time, that solid is going to melt because sodium chloride, an ionic substance, an ionic solid, has a very, very high melting point. It would take a lot of energy to convert that from a solid to a liquid. Okay. Then I've got, imagine that NaCl, sodium chloride, table salt, but as a liquid. And I'm not talking about sodium chloride like salt water. I'm talking about melting sodium chloride. Okay. That would have an even higher boiling point. So that sodium chloride's boiling point is going to be even higher. Takes a lot of energy to get that table salt into a liquid, and even more energy when it gets to go from a liquid to a gas. So everything would basically be shifted because of these extreme conditions that it's under. And that would be an example of a molecular or an ionic substance. Now, they can conduct electricity when they are liquid. So that's pretty powerful. Now, molecular substances. A molecular substance is a gas, liquid, or a solid at room temperature. A molecular substance is going to have a low melting point and a low boiling point. This molecular substance at that low melting or boiling point is not going to conduct electricity when it's a liquid. So a molecular substance like methane, for example, well, methane, butane, propane, any gases that we regularly use for igniting things, those are going to have low melting and boiling points. They're going to be a gas at room temperature. So that tells you, I always think of like a phase diagram. I got to switch to the pen feature, a phase diagram. And we've got pressure and temperature. And this phase diagram typically looks a little bit like this: gas, liquid, solid. Okay, so those are our gases, liquids, and solids. And I always like to think about, okay, if I got like propane or something like that, at room temperature, I'm right out here because it's already a gas. Now, what that means is, could I get it to transition? Could I get it to, let's apply that terminology. Could I get it to become a liquid? Yeah, I could. And what's that phase change called? A gas to a liquid? It's a condensation, or that is an that is condensation. So that's where I get my gas to become a liquid. Then my liquid can become a solid. And how's that going to happen? Well, again, if I'm staying on one flat line there, what am I doing to my temperature in order to achieve that? I'm getting my temperature to drop lower and lower and lower. And that event where I'm going from a liquid to a solid would be freezing. So these melting and boiling points, if I select this point right here and this point right here, well, those are considerably lower than the melting points and boiling points for water. That's in part because of those intermolecular forces that are holding water together as opposed to holding methane molecules together. Okay, everybody, this is where I wanted to stop. We got a couple of top hat questions. We're going to take off on Friday, or we're going to pick up on Friday with that last slide. Or sorry, not last slide, but the one that I just showed and then took away. So this slide right here, ionic versus molecular solutions. We're going to talk about that on Friday. With that in mind, like I said, I'm going to get you your exam grades and my video walkthrough posted to Canvas later today. So expect an announcement about that and then expect a notification whenever your grades are ultimately released. Then I'm going to be posting one of those quiz homework type of things on Canvas later today. So that will be up and that will be up until Sunday. I'm going to post another one for Friday. I'll post that, no later than Friday. Hopefully it'll be up today, but that will also be due on Sunday. So we've got two assignments that will be due on Sunday. So what you can look forward to from me is communication on the exams, then two assignments, and that'll do it. Yeah, is that right? Exams, grades, and the video, two assignments, and then we'll talk again on Friday. So I'm going to go ahead and stop my share. I'm going to stop my recording. And